Here's the video.
I'm Carl Papon, and I'm the main dev behind SpinalHDL and VexRiscv. And now I will do a demonstration about VexiiRiscv running on FPGA and booting Debian. So let me show you the FPGA dev kit, my table. It is with some, here you see some USB host port, audio output, HDMI output there. So because it will take a bit of time to boot, let me already start the process, and at the same time I can then tell a little bit more about the setup. So let me reduce this like this. So here is a serial port of the FPGA board I will just use at the beginning to boot it. And behind you can see some noise. That's the HDMI output of the board. So let's boot the system. Okay, here there is a LaTeX BIOS loading the Linux kernel. Here is Linux booting. Now it's switching to the HDMI output. So let me disable this. Okay. So, and here we are. So now Debian is running. There is systemd loading all the services, so it will take a bit of time. On this board, now there is a quad-core VexiiRiscv with 256 kilobytes of L2 cache. The HDMI output you can see now. USB host support I will use later for the mouse, the keyboard. And through USB host there is as well the audio output with a 3.5mm jack. The file system is on a SD card. The main memory is some DDR3 500 megabyte. The SoC which hosts the system is based on LaTeX. So LaTeX provides all the peripherals, the DDR3 controller for Vex2 to run on. There is as well JTAG debug to load binaries or debug with GDB remotely or things like this. I don't know if I said it already, so the system is running at 100 MHz, so the FPGA there, the RTX7, so it's an old FPGA, and on that dev board it's unfortunately the slow speed rate, so it doesn't really help. But here we are, logged in. So, let me, oh yeah, I need to plug my USB to the board. My USB keyboard was still on my desktop. I need to switch it now. Okay, now I have the USB. Meow, meow. Yeah, that's one thing. It takes quite a bit of some time to log in Debian. It seems it's because of systemd, because when I logged in all the system like Buildroot or Alpine Linux, it's really fast compared to that. But we should reach, yeah, user space, hello. So here I have a folder with a few demonstrations, including a boot script that will start X11 and then start a desktop manager with a few widgets for the fun of it. So let's go. And I think this will move a bit there. So we should see the mouse as well as the terminal, which is what you get if you start X11. Here we are. And then Window Maker. So Window Maker is an old school desktop environment which has annotated to be quite lightweight, and I have quite a few basic features. And yeah, here we go. So this I can close, and here is our terminal, and here is a few demos. So starting with CPU info. So yeah, here we are, quad-core, NeoFetch. So NeoFetch takes quite a bit of time, but if you try it on your desktop, you will see if you time it, it still takes like half or a third of a second. So it runs slow, it's normal. So here we are on Debian. Maybe I can start, here you can see the CPU occupancy for each core. I will start another terminal with htop. So htop, here we are. What else? Like this. Can it nyan? Here we go. Can it run Doom? I should call it Doom. So here we are. So yeah, I didn't enable the sound because when I run it with Doom, it takes quite a bit more time to start because you need to cache all the sound. So let's run instead some MP3 player. MP3, here there is this sound. And meanwhile, one thing we can do, I will reduce. I need more screen space. Here we go. One thing which is great, and not that common, especially with FPGA software, is the ability to run path. So path is an utility to diagnose performance bottleneck in applications. And let's, for instance, run it on Doom. Here we go. Bigger, very important, but things to the language. Okay, here we can see, like, for instance, branch miss, 4% only. It's not much, but Doom is not really, it's not really hard for you to do right branch prediction. Here we can see the number of instruction per cycle, so 0.7 is really not that bad. So yeah, whatever, let me kill Doom, stop the sound, stop this, and play a video. So for that, you can use mPlayer, for instance, a multi-threaded version, where we can play Big Bunny here. So you will see it will take quite a bit of time to start. The reason is, in distribution like Debian, packages are compiled in a way to reduce shared objects which come from other packages. So when you start big application with a lot of dependencies, they tend to have a lot of shared objects to run at the beginning, to load, and that takes a lot of time, like about 30 seconds for mPlayer. But we should get there. Here we go, we are in. So, yeah. So you can see down here the CPU are kind of quite busy, but it plays, the sounds stay in sync. But yeah, that's it. So, and now the slides. So, XPDF. It is COSCUP'. Oh yeah, and I will reduce this because some slide need already all the space. Here we go. In full screen. Okay. So some slide will take a bit longer than others to load, when they have images, but it's usable. So, yeah, just here a fast recap of what is the SoC that we are running on. So it's based on LiteX for all the peripherals. For all the peripherals, it's mostly LiteX. There is a quad-core 64-bit RISC-V with GC extension. That's mandatory to run Debian currently on RISC-V. So G mean they have FPU, MMU, atomic, multiply, divide, and C mean instruction can be compressed into a 16 format instead of 32-bit. For FPGA softcore, it's a bit unfortunate, but that's the situation right now. There is 256 kilobytes of L2 cache, instruction cache and data cache for each CPU are each 16 kilobytes, 4 ways, RTX7 FPGAs, low speed rate. This full SoC use 65,000 LUT, around 200 MHz, and there is a few. Here is all the memory current agents. USB host, user DMA, MMC, user DMA, HDMI directly has access to the DRAM. That's how LiteX is designed right now. And a few other peripherals. Yeah, it will take a bit of time, but there was another talk this morning which explained how to bring up Linux through OpenSBI and then Linux and how those things works. There is here as well in this SoC the Slint and the Plick involved that process for the interrupt between the CPUs and the peripherals, and here to provide timer and software interrupt between the CPU. And so, okay, here is the current VexiiRiscv feature set. So yeah, it supports 32-bit and 64-bit. It's mostly designed for FPGA, but I guess it could be targeted for ASIC without too much pain. Another extension I haven't mentioned which implemented is bitmanip. It can run Linux, Build, Debian. I also tried Alpine Linux last week, it worked well. And optionally you can set up it to have multiple issue. That means that the CPU instruction multiple like 2 instructions per cycle, it can be done. It will reduce the maximum frequency, it will increase the number of instructions per cycle you can do, so it really depends on the workload you want to run. You may want or may not want that. There is also the option to have a late ELU. That's a concept that you can have a normal early ELU, stage 0 of the execute stage, and you can have a second ELU in the same pipeline to execute instructions which will have late dependencies resolution, like if, for instance, you do a memory load, and then add something on what was loaded. That's a late dependency because memory load will come late in the pipeline, so you can't run the early ELU the next cycle the load started. But a late ELU, yeah, you can do that. So that's one trick to get more performances, which can be enabled. And if you turn everything on, performances can be quite high, but I would say it really depends on the workload and how things are compiled, because multiple issue CPU which are in order are quite sensitive to how things are compiled and dependencies between instructions. So keep that in mind. So for this demo, it is a single issue with no late ELU running. So the whole project is free and open source. There is no dirty business model behind. It's really true to the spirit. It also supports the RISC-V official JTAG. There is a light export. And then, yeah, now I'll talk a little bit more about CPU architecture to get more performances in the context of in-order CPUs. So the branch prediction is an important one. we have seen before when I was running perf, only 5% of the branch were mispredicted, which is really not that bad, but it's chocolate doom. It's not really hard to predict. But anyway, branch prediction is not really well named, I would say, because it's more than just predicting if a branch will be taken or not taken. There is first, before predicting if a branch is taken or not taken, you first have to predict if the instruction stream you are fetching contains branch instructions. You need your branch prediction to run even before you know what the instructions are, so really early in the pipeline. And to do that, you have the BTB. So the BTB will predict in the instruction stream what part of the instruction stream are branch prediction, are branches, or are call, or are return instructions. And it will also predict where they would branch if they are taken. So that's the role of the BTB. And then, for instance, you have the G-share predictor, which will only be useful for branch to predict if a given branch will be taken or not taken. And I will not go too much into the data here, but that's the main idea. Having really early in the pipeline of branch prediction to keep the instruction, keep the CPU pipeline feed with instruction. There is another thing, which is instruction cache prefetcher. So it really depends on the application you are running. If you are running an application which is processing data in a loop all the time, you don't really have issues with instruction cache having too many cache misses. But if you run big application in Linux, which have a lot of code base to go through, like running, for instance, OpenTTD or this kind of things, you start to have the issue that, yeah, CPU is waiting a lot of time on instruction cache misses. And so to fix that, either you make a really much bigger instruction cache, either you implement some prefetching things. And so in Vex2, that's something which was added. When you use instruction cache and you have a miss, it will trigger a cache refill. That's normal. But this cache refill is non-blocking. That means you can have multiple cache refill at the same time and still have requests coming into the instruction cache. So that's one thing. You have multiple slots of in-flight CPU cache refill. And when you have a cache miss, the prefetcher is also informed that there was a cache miss. And so the current implementation is that when there is a miss on the instruction cache, the prefetcher will trigger a prefetch for the next cache line. And then if, for instance, the CPU executes some instruction on a given memory block, and that memory block appears to be the one that was just prefetched before, then the prefetcher will trigger the prefetching of the next cache line, trying to stay ahead of the needs. So that's one thing. It's really not a complicated design, but it can already make a quite big difference. Still, it really depends on the workload, but on some it really makes quite a big difference. So, and then there is as well a data cache prefetcher, and here are some performance numbers to illustrate how much it can be impactful. So when the LiteXBO starts, it does some memory benchmarking, and without the cache prefetcher, write speed is, for the CPU running at 100 megahertz, the write speed is 168 megabytes per second. Read speed is 113 megabytes per second. But when you enable the hardware prefetcher for the data cache, you get really a big boost, especially in read speed. You more than multiply by 3. And you nearly multiply performance by 4. So yeah, it can be really impactful. How it translates into a real world scenario, I would say it really depends your use case. On Chocolate Dome, for instance, it boosts the speed by about 20%, if I remember well, 20% more frames just by having a data cache prefetcher. So, and it's not an expensive design to do. And it's a bit like the same for the instruction cache. You have your data cache and you have multiple slots for refilling a cache line with new data. You have multiple slots for in-flight write back of dirty cache line you need to remove to make space. So yeah, you have to design where you have a non-blocking data cache, and each time the data cache is accessed by the CPU, the prefetcher gets notified, and he will maintain a table of what was the last instruction at that program counter, like it was a load, it was a store, and at which address that memory loader store was accessing things. What was the delta in address between the previous access and the previous one? Like for instance, if you do a memory copy, you may have like 4 byte offset between each access, every time 4 bytes, so you have a stride of 4 bytes, and you have a score to, for instance, figure out, is that always the case? Is my access to that instruction always doing a plus 4 bytes access pattern, so it's really reliable, so I can do a lot of prefetching on that instruction because it's always doing the same. So yeah, you have this kind of structure where you have tables to keep memory of what happened in the past, to take decision if it's good or not to prefetch some cache line when these things happened. Really can be really impactful. And another aspect of the whole system is its memory system. So there is memory currency between all the CPUs and the DMA in the system, except the HDMI, but that's something else. But there is also the concept that all the memory interconnect is running out of order. That means if a CPU writes a given address and use the cycle after send a request to read the same address, you don't know what you will read back because things can execute out of order. So the memory interconnect may first do the read and after the write, even if you request things in the other order. But this can seem tricky to implement, to handle, but in practice it's really not that hard to handle, and it has really a lot of great upside, especially when you have an L2 cache. When you have an L2 cache, you have the memory access latency can vary greatly. Like if you have a cache hit into the L2, the memory latency can be like just 5-6 cycle latency. But if it misses the L2 and has to go to the DRAM, you may have, at best case, to that SoC at 200 MHz, best case you have 20 cycle latency. More generally, you have 30 cycles, and it can go up to 100 if the DRAM is doing some refresh and things like this. So you really need this kind of memory interconnect, being able to work out of order in order to keep things flowing in the system, to not have one L2 cache miss holding everybody else behind. And so it is based on tiling. And yeah, that's it. So looking for contribution if you are interested. Really, it's a big project. I haven't talked really a lot about it, but one of the ideas is really to cover a very large design space. Here is a Debian design space covered, but there will be a lot of room for more simple system to improve performances, testing, maybe trying to port this kind of system on ASIC. Here is a repository. There is an issue, the number 1, which is tagged. If you are interested about the roadmap or want to contribute, you can come here and talk, no problem. And here is some documentation about how you can reproduce what I'm running now on the board. If there is something missing, again, come open a GitHub issue. And as well, thanks. It's hard to find good funding for this kind of project, and I would say thanks to Anna to provide the funding, open source funding. So thank you, and now the question.
Okay, so here we are going to call our speaker. Sorry that is so messed up. Come on, Charles, he's still there. Hello, Charles, can you hear me? Yeah, we can hear you some as well. Do we have any questions here? Okay, I have a question. Finally, there is official RISC-V JTAG. So I'm just curious about how was the decision to transition from your own RISC-V OCD to the official JTAG. Is that what is the design choice?
OpenCD. So that's one part of it. For simple debug, the VexRiscv custom debug was really good because it was really a lightweight one. But when it was starting to be more advanced debug, yeah, it was really a pain to maintain as well. That's mostly it, yeah.
I see. So do we have questions here? I think that there's actually a student also developing his own RISC-V core. Do you want to? By the way, Charles, is your Debian port official, or did you rebootstrap it from the source?
So, what do you mean? I'm not sure to understand exactly what you mean by official. What I did is I built the images using a few Debian utilities.
I mean, if I remember correctly, that Debian currently don't have the official image, and
yeah, there is no. I didn't took a already built image. I had to assemble it. I did assemble it.
Oh, you need to assemble it yourself. Okay.
Yeah, in case of, if you're interested about those things, in the VexiiRiscv repository, there is a doc folder, Debian, and here there is all the steps to recreate the image, and it's mostly based around the tool, which is, yeah, debstrap, that allow you to create a Debian file system. And then you /root into it, and you can tune a few of the things.
I see. Thanks you a lot. By the way, can your CPU run Doom now? I mean, there is a student under there.
Sorry.
I'm trying to make a connection with the audience because we have previous speaker also putting his Linux on his own core. Yeah. So I'm trying to teach him that because your core, your VexRiscv can run Doom, so I'm teasing him that maybe his core can run Doom too. Is it okay to run Doom?
Haven't tried.
You haven't tried it? You should definitely try it. Anything should run Doom. So I guess there are two students as well. We have been discussing a lot when Charles is talking about cache system. Do you have any print prediction or cache system design you want to discuss? No, not really. Okay. Oh, by the way, Charles, I have a board on my hand that this one is the eFabless. Yeah, it actually have a VexRiscv version 1 from your core. So do you plan to do the ASIC or just let someone else to do that?
For Vex 2?
Yeah, for Vex 2.
I'm not planning to do myself an ASIC because I have too many things to maintain and handle. It's too much of a burden. I should really try to stay focused. So I'm trying to not dilute myself with too many projects. So like if somebody is interested, I can help with making the VexiiRiscv more ASIC ready, maybe with all the shit about register file and memories and things like this, to black box them. But overall, no. I'm trying to focus now really on FPGA.
I see. Okay, so I guess currently we have no more questions here. Okay, so very thankfully for your talk that you have been presenting to COSCUP for 3 years. Maybe next time I will fly to Swiss and get down to you and have a drink with you too. Sorry, and sorry for the network connection this year. That is really beyond my control. Yeah. Okay. All right. Okay. See you. Bye bye.
Thank you.